Okay, so here, I was just finishing up this one. We have a positive, negative, right? You can put it together as one coordinate. Positive, negative, root 15 over 3 minus 2, comma, 1, and you get the y value from here. Right, so please write, don't waste it, right? Points, not the x values, right? So it's points, you have to write as a coordinate, and you get the y value from what you began with, the y value from there. So that gives me 1, 2, 3, 4 invariant points there. Okay, so now we know how to find an invariant point algebraically. Let's look over the whole graph, and we're going to go over all of the words from up here. So all of these words we're going to do right now. Again, there are 4 steps I want you to do. 1, 2, 3, 4. It doesn't matter the order, right? Doesn't matter the order, but we want to do these 4 steps. So I'm going to start with invariant point, which we did right here. Invariant point means, okay, and I'm going to highlight that in invariant point. I'm going to do in the purple here. Copy. So you're going to look here. Actually, I'm going to do it red so you can see. You're going to look at this graph. Wherever I see y is 1, so when y is 1, right, y is 1, go to your line function wherever it is and draw a dot wherever I put it. I know it might not be perfect. It might not be exactly at a solid integer number, but that's okay. Wherever I have the line, I want you to find 1. Put a dot. Okay? Here, I want you to find y is negative 1. Go across, use your eye, and draw a dot on the line on that y is negative 1. Does that make sense? Okay, so on this one as well. So we'll do both. Look, when y is 1, 1, you go across either way, and you put a dot on my graph wherever I have it. Does that make sense? Okay, you seeing the pattern? And then here, go look for negative 1, and go across to the graph and put a dot wherever my graph is negative 1. Those are invariant points. That's going to be my intersection point between the original function and the reciprocal of this function. So those ones will be on both the graphs. Okay, so these dots here. So that's my invariant points. So get used to that word, invariant point, or it's called point of intersection. So they call point of intersection or invariant point. So either way, right, they're points, so it's called point of intersection or invariant point. That's what those are. So it'll be on both the graphs, both the reciprocal and the original. Okay, what else? So I have that one step done. So remember, there's 4 steps I want you to do. Doesn't matter the order. Wherever the graph increases, it's going to go decrease towards the 0, the x-axis. So for these graphs, let's say when it's linear like this, it's going up, it's actually going to be heading downwards. Where it increases, it decreases. This is going to have a horizontal asymptote. See it where it increases? So I'm going to put a horizontal asymptote right here. And they said, even as a hint, anything that's linear will have a horizontal asymptote. Anything that's quadratic, or these 2 shapes, will have horizontal asymptotes. Plus, other ones will also have horizontal asymptotes. So not just linear and quadratic, but because it increases, it'll become decreasing. Same with this one. So I'm going to put a horizontal. When I draw my horizontal asymptote, I also want you to put the equation. I'm going to highlight that. Do not lose any of these silly wasted marks. Draw it, label it. Draw it, label it. Draw, label, draw, label. I don't need you to label the invariant points unless it says to. If it doesn't, you don't have to. So we're going to go here, dot, 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 y equals 0. Draw it, label it. When you draw it, please label it. There we go. Dash line. Okay, so they said specifically, definitely lines and quadratics will always have a horizontal asymptote. Okay, that's 2 of the 4 steps. Another step they said above, so again, we're going through all of these lovely words above. So we have horizontal asymptotes for any linear or quadratic. We did the invariant point. That's one of the steps. I want to look for vertical asymptote. The vertical asymptote, I'm going to do that in light blue here, is wherever it equals 0. Wherever the graph equals 0, then the reciprocal is going to not be defined, which means it's a vertical asymptote. So wherever the graph hits y equals 0, I'm going to draw a vertical line, dashed line through here. That's going to give me a vertical asymptote because it's not allowed to be the reciprocal of that 0. So, and label it. Draw it, label it. This will be x equals negative 3. So when you draw it, Please label it. Draw and label, draw and label. For this guy, wherever it's 0, right? So wherever I see that 0 here, I'm going to draw this line like that. And it's right here. Okay, and you know I have the point over here, so it's supposed to be those 2 points. So usually I would put a little dot there to assure you that it's there. Okay, so you've got that. So wherever, right, it hits 0, you're going to put a vertical asymptote. So again, draw it. What did I say? Draw it, label it. So x is -5. Draw it, label it. X equals 1. Draw it, label it, draw it, label it. Please don't lose any marks for not labeling it with the equation. And usually we will put like a dot there showing you that it actually goes through that point. I know sometimes you're like, does it or not? Okay, unless it's a step pattern or something. Okay, sometimes you got to look for the step pattern. This case, I would probably just label it like that. Okay. Now, what else do we need to know? All the other words here. So when it says, so the words here, it said the in-between words, it stays positive where it stays positive, negative is negative, and the increase, decrease. So if it's positive here, so if the y values are positive, then the reciprocal will also be positive. So from here, I'm not going to graph it down here. No, the y values aren't changing from positive to negative. So see how the y values are negative here? It'll stay here in the negative area, right? So it'll stay where the graph was. It's not going to flip over. Same thing here. The y values are negative, so the graph, my reciprocal, will still be here. The y values are positive, it'll still be here, right? So it's not going to switch from negative to positive. The other thing I said was, as it increases, the reciprocal will decrease. So I think of this as it's heading away from the x-axis, right? It's heading away. Look what happens to the values. As I go to 4, the reciprocal is 1/4. As I go to 6, the reciprocal is 1/6. As I go to 10, the reciprocal is 1/10. It's getting lower. So as it heads away from the x-axis, the reciprocal is going to be heading towards the x-axis. So away, which means it'll do this. And it becomes a little asymptote heading towards the x-axis. Getting as close as possible. It won't reach it, but it'll get close. Okay. Then the opposite is true here. So see this line? On this side of my invariant point, it's heading, see how the line is heading towards the x-axis? It's getting lower. If I said 1/2, what's the reciprocal of 1/2? 2. If I got closer and said 1/4, the reciprocal would be 4. As I head towards the x-axis here, the numbers are actually heading away. So it's getting away from the x-axis. So as they get lower, they get higher. As they get higher, they get lower. Reciprocal. Yep. Yeah. Okay, next. That's good, right? Other side, let's do it again. Okay. As it's getting lower, heading away, it's actually going to head towards the x-axis. See how it's the reciprocal of what's happening? And then look, this is heading towards the x-axis, but the reciprocal of that, right, as the numbers get lower, 1/4, 1/2, it's actually further away. So it's going to head away. Good? Giving you a chance to catch up on the diagram. We're all right? Okay, let's try it again on this side. And that's it. That's all we get. It's very not satisfying. What was step 4, or the 4th step that I didn't do? Right, I did asymptote, asymptote. So there's 2 asymptotes, so it's easy to remember. Asymptote, asymptote, invariant point, which I started with, it's this max-min. If there's a maximum or minimum on the original graph, there'll be the opposite on the new reciprocal graph. Is there a max-min on my line? No, so there won't be one. is there a max-min on my quadratic? Yes. So here, okay, you can see the orange. Okay, so this one here, I have a minimum at -2, -4, true? Okay, that's going to convert to a maximum at same x value, and then what's the reciprocal of the y? -1/4, right? I don't need to see this one, so you don't have to write that one, but I need to see this, so you're going to write that down. We always ask for this, so it's better to have it down and just get in the habit. So the 4 step, you always look and say max min becomes the opposite. And then you're going to go and point to it. So I don't need it labeled in it. Sometimes the graph is too hard, so you're just going to say it's right there. So you can just draw an arrow. So I don't need this one, but this one, yes. You're going to tell me where the max or min value is, and then the point is somewhere over there, right? I'm going to draw it now. So I want to draw that point. Okay, we're going to draw the point -2, -1/4, which will be right here, somewhere really low. Okay, so you kind of draw the arrow to there and try to show it to me. I know that it's not perfect where you're drawing it, right? I know it's not perfect, but you're showing me by the point, okay, by the point where it is, okay? So that's why you got to label it, because I can't see where a quarter is. Yes?
How did you get the local maximum again?
You're going to take the minimum value right here. So this one here, we know wherever there's a minimum on a graph, it'll convert to a maximum of the reciprocal function. So minimum is going to be at -2, -1/4. I take the reciprocal of this value. Yes. Okay, does that make sense? So I'm going to go from -4 becomes -1/4. Good? Does that make sense? Yes. No, that's what the function is. So you remember the inverse. Inverse means you switch x and y. Reciprocal means you're switching the reciprocal of the y value, right? So that's the reciprocal function. You take the whole, wherever the x value is, but you take your answer and you switch it over, okay? That's what's happening when you did the linear. So when you had, so if you had y equals x compared to y equals 1/x, when you have your table of values, what ends up happening, so if you have your x and y, so if I said 2, and x is 2, on this one, x is 2, and it's 1/2, right? And I did 3 of the original. So this is actually the reciprocal function of the x. If I said 3, when I did 3, 1/3, look, so it's only the y value that flips, right? So the x value is whatever you input, and this becomes the reciprocal. So this is the relation we're trying to do, but for any function now. So we learned this one, and we kind of just memorized this, but it's actually this is the reciprocal function of the x. We always called it the reciprocal function, but we kind of went, reciprocal of what? Of the x, right? So we never learned it this way, so it kind of relates the two together. So they're saying, oh wait, if I just took this one and I flipped all the y's, that gives me my reciprocal function. Yeah, does that make sense? So again, we never defined it this way, right? When we did the reciprocal function, we said just memorize it, there you go. But the word reciprocal is reciprocal of what? Like, it's reciprocal of the x function. So now we're doing it for any function. So I would take this quadratic, and that's what we're going to get to by the end of this 5.1. We're going to say, I'm going to give you the function and write the reciprocal function and go from the equation back and forth. So we'll get to that. Right, so we'll go back and forth. But that's where it comes from. Sorry, I know I should have done that at the beginning, but yes, I forget. Okay, so does that make sense? So we're taking, keep the x, switch the y. Keep the x, switch the y. Okay, so then we know the point is somewhere there. I know it's hard to show a quarter. Wait till the next one. I think we have 1/9. You can't show it. So put the dot and then put an arrow and say, look, I'm showing you what I meant for it to be. All the reciprocal numbers are going to be awful. Like they will not be accurate. Just that's why you need to label it. So I do need to see you label it and then give me the arrow. Okay, now invariant means that it's on the same one. So see how it's heading away from the x-axis, which means it's heading towards. So look, heading away means it's heading towards. That's the way I always think it. Where it increases, so the words here, where it increases, it decreases. Where it decreases, it increases. So look, where it's heading away, it's heading towards. So increase becomes decrease. Here, this side's decreasing towards, so it's heading this way, up. Right, so it's opposite. So it's heading towards the x-axis here, this little corner here, so it's heading up away. Okay, try this side. So as it increases this way, it's now going to be decreasing this way. as it decreases on this side, it'll be increasing up the asymptote. And they will look very kind of squarish and like you feel like you're not curving it enough, but that's just the way the reciprocal functions look. They look very kind of square, almost rectangular sometimes. Okay, here, we're going from this dot. That's an invariant point. So notice how I'm trying to pass through that point. You have to pass through. That's the intersection point. So I'm going to go from here, curve it out, and get to that point. Okay, it looks very wide. I know that's just the way they look. And then look, this part is heading towards the x-axis. See this part right here looking? Okay, which is heading away. So this part's heading, and now it's heading away. It's the opposite. So this part's heading towards the x-axis, so it's the opposite, it's heading away. That's what the graph is. There you go. I know. And you go, what did I just graph? Yes, there you go. That is the reciprocal function of that quadratic. Pretty. Any questions? Let's try it a couple more times. I know. It's the weirdest looking graph ever.